let's work. It's my great pleasure to start the morning session, and Silvia Toffoli, who is a professor at the university, a scholar normally superiore of 5 years, or something like that, will give the first talk. And Silvia is one of these. Silvia has a very full of awards resume that you can read about, but I thought the most exciting thing is at the end of it, she says that she has 2 PhDs, one in mathematics and one in philosophy. And both extremely important institutions. So her PhD in philosophy is from Stanford, and her PhD in mathematics is from Berlin. So it's a great pleasure to welcome you. Great.
Yeah, thank you so much. Thanks everybody for being here. Today I'm going to talk about diagrams. So I'm going to give you a kind of preview of my forthcoming book with Oxford University Press, How to Prove Things with Diagrams. I still didn't finish the manuscript, and at the end I would like to have some kind of remarks on how diagrams can be also integrated into formal mathematics and stuff, so I'm very eager to hear from you. So this talk is not directly connected with the topic of this workshop, but it's indirectly connected. I think some of the things I'm going to say could resonate with some of the things that interest you on how to integrate different type of notation, etc., and what is the process of formalization. So until the very last moment, yesterday, I was unsure which talk to give. So the first title was Structuring Mathematics, that was totally different, about how we can be sure our purported proofs are correct. But since so many people showed interest on diagrams, I thought might as well just talk about the diagram stuff. So I'm sorry if some of you already saw some version of this before, but many of you didn't. So here it is. So here is the plan for today. I'm going to give you just a general introduction and then discuss a little bit in detail 2 different examples or case studies of diagrams in mathematics. And one is diagrams for surfaces, and the other one is commutative diagrams. And then at the end, I'm going to talk about some philosophical issues that emerge when we are thinking about the role that diagrams play in proofs. And in particular, I think a very kind of important controversial point I want to make in my book is that diagrams, in some cases, can be essential to the proofs in which they figure. And of course, what does this mean? What does essential mean? Of course, it doesn't mean that we couldn't prove the same result without diagrams. Of course we can. So there must be some other meaning of this term. So in order to assess whether a diagram is essential to a proof, we have to work with some criteria of identity of proof. And the kind of basic idea is that there are plausible criteria of identity of proofs according to which if we convert a diagrammatic proof into a non-diagrammatic proof, then we are not just creating a different presentation of the same proof, but a different proof altogether. And I think this is a plausible claim, but I'm going to try to make it more clear later. So let me just start with a kind of general introduction also to kind of give you a sense what philosophers think about when they think about diagrams and what is the source of the skepticism, what are the type of criticism I'm replying to. So a lot of people, in the philosophy of science, it's very common to distinguish between the context of discovery and the context of justification. And nobody denies that diagrams are very helpful for discovering. We can use them as heuristic devices. Everybody agrees that, uncontroversial. The very problematic thing is, can we use diagrams in the context of justification really to justify, establish some mathematical propositions? That's very controversial. And there has been a lot of work actually in the history of mathematics also focusing on diagrams in geometry. And a lot of works have established that the use of diagrams in Euclidean geometry, for instance, is highly regulated. Ken Menders did that, and then there is a very influential work by Jeremy Avigard and John Mumma. They also created a formal diagrammatic system for Euclidean geometry. And so it seems to be that diagrammatic reasoning is reliable and leads to stable results there. However, as we all know, in classical analysis, the use of intuition and diagrams can lead us totally astray. So there's like this famous public lecture given by Hans Hahn in the 30s called the Crisis in Intuition, in which he gives plenty of examples of why our intuition is actually not a reliable guide to truth in analysis, for instance, like space filling curves, continuous nowhere differentiable curves, etc., all this kind of stuff. So one idea that philosophers had after this is that, okay, perhaps diagrams can be allowed in Euclidean geometry, but not in more modern branches of mathematics. And like this crisis in intuition, in some sense, led to a ban of diagrams. So intuition was related to diagrams, and so the thought was, okay, intuition leads us astray, so better do everything without diagrams. Still, people say diagrams are still nice things. In fact, they can still enter into the context of discovery, and they could be seen as tool for speeding up communication. In a very influential paper that was mentioned also in the lecture last night by Thurston on Proof and Progress in Mathematics, he says, mathematicians use wide channel of communications that go far beyond formal mathematical language. They use gesture, they draw picture and diagrams, etc., to suggest, okay, when we communicate with the member of our subfields in order to speed up things, we can use diagrams, etc. But maybe they are not like so essential in some sense. So here is like a great statement of what I want to argue against. And I think it's really nice that someone puts it clearly, so I have a clear target. So here's John Burgess, a very influential philosopher of math from Princeton, in a book, Rigor and Structure, from 2015. He says, some diagrams are surely no more essential to the proofs in whose midst they appear than the illustrations that accompanied many Victorian novels on first publication were essential to the literary value of those works. So here is the illustration of the Mill and the Plough by George Eliot. Other diagrams may play a more important role, especially perhaps in this type of abstract algebra where what is called diagram chasing is ubiquitous. Though even here, the kinds of diagrams that are chased seem only to abbreviate information that could be put more cumbrously and in more or less way less easy to take in words. So the idea, either diagrams are really kind of just extra devices like the illustrations of novels, or they are like this type of algebraic diagrams that at the end, they're just we can translate them in words without losing anything important. So that's kind of the orthodoxy in the philosophy of mathematics. It's not a minority view. So what are the claims I'm going to argue against? So the skepticism about the role of diagrams in proof. One, diagrams, like other devices mathematicians use in their reasoning, can be disregarded as epistemologically irrelevant alternative ways of presenting information that can be conveyed in words. So the idea is diagrams are just notational variants. If I write a math text in Times New Romance or Arial or Comic Sans, it's the same thing. It's just like notational variants. And the idea is all notations are like this. And obviously that's totally mistaken from the point of view of the practicing mathematician. But here I'm really discussing with the philosophers. That's why maybe things that seem obvious to you are not obvious in general. So I reply is sure, propositional content might be invariant, but propositional content is not all that matters from the point of view individual justification and knowledge for the epistemology of mathematics. And the second kind of assumption I think underlying this type of criticism is that there is no principled way of distinguishing reliable from unreliable use of diagrams. And in fact, yes, there is. It's just we have to find it out and articulate it clearly. So here are my main theses. One, some diagrams form mathematical notational systems and therefore can play a non-redundant role in proofs, so they can enter in proof and enter the inferential structure of proof without affecting the rigor of such proofs. And these I'm talking normally of informal rigorous proofs, not the formalized counterpart, although there are formalized counterparts as well. And two, there is a plausible conception of proof according to which diagrams are not just abbreviation for more cumbersome non-diagrammatic displays, but can be essential to those proofs. And I'm going to work with two simple case studies, and I have a lot of slides and not a lot of time, so I'm going to, since this is a mathematics audience, I'm going to be very quick with the example, but just to give you a sense of some cases. So here they are. So the first is kind of a simple exercise, let's say. So here you probably are all familiar with the Moebius band and the way of representing surfaces with squares with or polygons in which sides are identified. So here we have like an illustration of the Moebius band, and then we have an arrow diagram, and they are just like two different representations of a topological surface of the Moebius band. So then one question one could ask is like, okay, what happens if I cut the Moebius band along its core? So do you know the answer? What do I get? If you know the answer, how do you know the answer? So in fact, like when I ask my students, okay, how can you find out? So let's see, we have these type of representations. Look at that. Can you find out in your head what happens? Really hard. I mean, normal people can't do it at all. So what my students normally actually do, they build it. So they actually build the model, cut it, and then like find out what happens. So that's like one way empirical experiment. But certainly with that illustration of a like material Moebius band, it's very hard to work with. You don't have like a way to reason and find out the solution of this puzzle. What about the arrow diagrams? Actually, the arrow diagrams, you already see, oh, maybe actually with that, there is something I could work with. So for instance, I could start creating two arrow diagrams from one. And like, oh, actually with like this little diagrammatic argument, I can like cut and paste. And so if the task initially was like to find out what happens when I cut along the red interrupted line, I'm like cutting, oh, then I create those other things, and then of course I have to find other convention to make sure I identify correctly the things that were identified before. So I do that, and then I re-glue, and then guess what? I obtain a cylinder. So that's kind of a surprising claim and interesting. And it's something that, I mean, it's like a little exercise, but I can prove more complicated things with similar techniques. And the idea is like cutting and pasting is not, it's also intuitive terminology, but it's also corresponding to precise mathematical operations. So gluing corresponds to forming a quotient space, and cutting is the inverse operation of gluing. And in fact, you're gonna say maybe, yeah, like this looks too easy, so it seems like when you cut the Moebius band, you obtain like a simple cylinder, but I didn't say that, you obtain a topological cylinder. The way this cylinder is embedded, it's another story. And in fact, what are these diagrams telling us? So arrow diagrams do not give information about the embedding. So when I have like the Moebius band here, the first one, I just say like these two sides have to be identified twisted, but I didn't say how many half twists I did. Just any odd number would do, like following the instruction correctly. And so in this case, actually we would obtain a twisted cylinder, but still a cylinder. Okay, so obviously if we can identify two sides of the square, we can also identify the other two sides to get at surfaces without boundaries. So here, for instance, we start with a cylinder, and then we identify the other sides, and we obtain a torus. And we can go on like this. If we started with the Moebius band, we would obtain a Klein bottle. And in fact, turns out we can obtain all close connected surfaces in this way, just like extending the notation. And I think this is very cool. This is like this canonical way to represent close connected surfaces, orientable and non-orientable, by gluing the sides of polygons. And so you have a classification theorem that tells you you can do this. So they are all there. And in fact, how you prove this theorem? In the same way I proved like the little exercise. So here is a step of the proof by Massey, this graduate textbook, Geometry and Topology. Just to give you a sense, it's not only me that use diagrams, obviously, in topology, like you know already, but and here it's just like a step of the proofs in which like we have a configuration and we have to kind of go towards the more canonical configuration that I showed you in the statement of the theorem. And basically to do that, we do the very same thing I did before, cutting and pasting. Like it says, to go from 1 to 2, for instance, we cut along C and glue along B. So we imagine like cutting along C, we have 2 diagrams, and then we re-glue them along B, and there the B is like kind of the scar that you obtain when you glue them back together, etc. So you can do these like sequences of operations. So you think with the diagrams. The diagrams are not just like a static device to illustrate something, but something like you do operations with. Okay, so differently than topological sketches, arrow diagrams are topological diagrams with precise mathematical conventions. They satisfy well-formed desk conditions, and they are subject to precise rule of manipulations. So they are rule-governed. And in fact, you could go more in detail to describe it precisely what this cutting and gluing means in each case. But so one point that I think is very important, the fact that they are rule-governed and they satisfy well-formed desk condition means that they form genuine notational systems in mathematics. So, but what does it really mean to form a notational system? So I'm gonna make a little detour also, show you some knot diagrams because I'm obsessed with knot diagrams, so every talk has to have at least one knot diagram. So here is the discussion on notational systems. So arrow diagrams, first we can notice that they don't pose the risk of overgeneralizations that is typical to geometric diagrams because they are topological in nature. And I already mentioned, so the fact that they can be used reliably in proof is explained by the fact that they satisfy this well-formed desk condition and they are subject to precise rule of manipulations. And this is not a feature of them only, but of diagrammatic notational systems in general. So here is Keith Stanning, who has also written about the use of diagrams in logic and logic education. Systems or representations are set of objects like sentences, diagrams, films, each of which stands for something else. What makes for the system in these sets is that the representation bear relations to each other, which corresponds in useful ways to relations between the situation they stand for. So mathematical notational systems are representational systems of various kinds. They are systems of external objects deliberately invented as tools for communication and reasoning, endowed with an intended interpretation and use. So I want to exclude things like just like natural language, etc., but really focus on things invented with a specific aim in mind, like also algebraic type of notations, etc. And I also focus on written or inscribed notation, so I'm not going to talk about other notational devices such as the abacus or things like that, or 3D models. So another example is knot diagrams. So you're probably all familiar with what mathematical knots are. So they can be defined in different ways, but here, for the sake of simplicity, a knot is a smooth, closed, simple curve in a three-dimensional space. So they're just like abstraction of physical knots in which their ends are close together, and they are all intrinsically homomorphic to the circle, but the difference is how they are embedded in space. And obviously, in knot theory, we don't care about like the precise geometric properties of these objects, but really like how their knottedness. So one of the main aim of knot theory is like to classify knots and to, for instance, find out when two knots are equivalent and when they are not. And to do so, people use knot diagrams, and these are, again, control representations which display only a certain number of properties of a knot. So we start from a knot in space and we project it in a plane, and we keep information at the crossing of which strand goes over and which goes under, and we use a convention. We could use different conventions, and in fact sometimes are used different conventions. But this convention of having an interrupted line is particularly cognitively successful because it exploits some principle of Gestalt psychology according to which we have, it's very simple and natural for us to interpret the interrupted line as just like going under because of this principle of linear continuation. So this is, for instance, a knot, and we could ask, what knot is that? maybe like we can modify a little bit to see whether it's a simple knot we can recognize or not. I don't know if some of you recognize what knot is this, but you will find out later. And again, one important thing about notational system is what you can do with them. So elements of a notational system can be combined or mentally manipulated. So with arrow diagrams, we define this cutting and pasted, and also like we can define different operations. With knot diagrams, we have this Reiter-Meister theorem that connects basically the mathematics of diagrams to the mathematics of knots, and it tells us that any two diagrams representing the same knot can be actually transformed one into the other with a finite sequence of three simple local diagrammatic moves. But in practice, we don't need actually to appeal to this theorem, but we can appeal to a sort of our imagination of manipulating things in 3D space. So here, for instance, I don't have to appeal to any theorem to convince you that these two things, these two knot diagrams, actually represent the very same knot, right? Because, so it's just like the same thing. I take this strand and I notice, oh, guess what? That's like on top of everything. So I'm interpreting it in 3D, so I just like take it towards me and put it down. So like that seems like pretty straightforward. I can do that, and then, yeah, it turns out I can decompose that move into a sequence of local moves, but I don't need to do that. Okay. So some other philosophers have been pointing out that the importance of notation in mathematics, focusing on diagrams, but also algebraic symbolism or like numerical systems are clear example of how notations really does some work for us. And here's Mark Olivan discussing this. He says, it might be tempting to suggest that a mathematical object by any other name would be just as useful. But we have seen that this is not so. Sometimes the names encode properties of the object in question, and in such cases, other names would be less revealing. In short, properties of the notation are important to mathematics. So this seems absolutely correct and true, but also a little vague. So what does it actually mean? So it seems that not all properties are going to be mathematically important. Some properties are just cognitively relevant. So here I showed you this knot diagram, and for instance, like the convention used at crossing is relevant here because it allows me to interpret the representation correctly in 3D and to assess whether these two diagrams represent the same knot or not. So I can do that. But like the fact that it's black or red wouldn't change anything, for instance. So there are some properties that are not important. So I think it's crucial to distinguish between what I call enabling and constitutive feature of a notation. So each notational system presents clearly identifiable and reproducible constitutive perceptual features, like lines, interrupted lines, arrow, etc. And other features are just enabling. So the color in this case is just enabling. Doesn't mean that it's always just enabling. Sometimes the color encodes mathematical information in other notational systems. Even in knots, I can have like this invariant that's called tricolorability, in which I color each strand of the knot in a mathematically significant way. But with just regular knot diagram, that's not like a mathematical significant property, although it's cognitively relevant. So if I drew this thing in like light yellow, that for you would be, especially like from the one in the back, you can't even see it, then you would not access the representation. So it would be like cognitively important, very important, because you can't see it. Or the size, if I make it super small, you can't see it. But it's not something that carries mathematical information. And so it's really crucial to distinguish between these enabling and constitutive features. And that's like something that is obvious for symbolic system, but has been like controversial with respect to diagrams. And I think failing to make this distinction has led people to think, oh, like diagrams are just like subjective representations, you can't use them rigorously. In fact, you can, as long as you are very clear about what matters mathematically and what doesn't. And in historical practices, you could have been very clear without being explicit. Now we can also be explicit. Okay. Oh, well, it's already 9:30, so I have to go really fast. But I started a bit later.
8 minutes later.
So, but coloring Euclids, in the case of Euclidean diagrams, the constitutive features are what Ken Manners called coexact one. But just like to go quickly, normally again the color doesn't matter. But in fact, there are like some Euclidean diagrams, like this colorful diagram by Byrne in the 1800s. He had like this colorful edition of the first 4 books of Euclid, in which colors encode informations, and in fact, it doesn't need letters. So basically, like, I think there are some minimal constraints that this like constitutive feature has to satisfy in order for the system of representation to form a notational system. So they have to be clear. So the constitutive perceptual feature have to be clearly identifiable and distinguishable. They have to be reproducible, and the operation defined on the notation should be cognitively manageable. So I'm gonna be quick in illustrating this, but you can have a sense of like non-clear representation very easily. And here, just like quickly, like the exercise I asked you, what was that thing? In fact, is the unknown. So it's like the simplest knot, and you can prove that just by a sequence of manipulation on the diagram. But okay, let me just like go quickly to the second case study that I'm just gonna mention because I want to say something about the essentiality of diagrams. So the second case study, you already like know this, so I just want to recall to your attention that in homological algebra we can use commutative diagrams using the so-called diagram chasing techniques. So we have these diagrams, and then like we take elements, and in this case the nodes are abelian groups. We take elements and we like transform them around and see what happens to prove like certain type of properties. And these are the type of diagrams that Burgess was like, oh yeah, those diagrams are more essential, but in fact like same things could be done in words. Of course same things could be done in words, like it's very easy to describe that diagram in Word. But like if you think about like the type of reasoning that goes on, like to find out the proof, but also to establish a result, then it seems like pretty plausible to think that the two-dimensional layout of this thing is essential to that type of reasoning. In fact, like these techniques are called techniques by diagram chasing. Like you're like diagram chasing, it seems to suggest that a diagram is involved, that you need a diagram to do a diagram chasing. Okay, just very quickly. So yeah, you can chasing the diagram just means to take elements and like transform them around following the hypothesis of your lemma. In this case, like some F2 and F3, for instance, are surjectives, the row are exact, etc. So you just like follow things around like this, and you like obtain the result you want to obtain. But the idea is like you take elements and move them around the diagram in specific ways. And so it's called the 5 lemma that just establishes simple properties. But then like there are a bunch of proofs in homological algebra that exploit this technique. And in fact, a lot of books just show you one time how to do it, and then they say, okay, by diagram chasing you can find your thing. Like I leave it for exercise, and like even the fundamental theorem of homological algebra exploits this technique in various ways. So of course commutative diagrams do not present the problem raised by the use of topological diagrams because they don't appeal to any sort of spatial-temporal intuition, although we still reason exploiting their two-dimensional layout. And it's easy to see how these diagrams could be eliminated. But guess what? It's easy to see how all diagrams could be eliminated, because like all diagrams are like discrete things. Like non-diagrams, they have a discrete number of nodes, and it's very easy to code them as a sequence of numbers. So everything can be eliminated, but this doesn't mean that it can be faithfully translated. Okay, so just like quickly, there is still visual thinking going on in commutative diagrams, and I think like in a way, they are analogous to maps of like underground systems in which like you don't care so much about the geometry of these things, but you have like different nodes connected in different ways, and you have like to connect the two nodes or like find some properties. So let me go to the last part of my talk. about the essentiality of diagrams. I guess I won't leave so much time for discussion, but there are like some workshops in the afternoon, so I hope we can follow up that because I'd like to hear what you think about this. So, as I said in the introduction, to say that a diagram is essential to a proof, just for this statement to be meaningful, we have to understand what is a proof. And to understand what is a proof, we need to say how are proofs individuated. So in his blog, at some point, Gower said was thinking about explanatory proofs, and then he realized, oh, even the synonym or basic question, when are two proofs the same, was pretty hard to answer satisfactorily. In fact, there are like a lot of controversial examples about, for instance, a proof involving lemmas. I have one lemma before the other. If I change the direction of the lemma, is the same proof or not? Yeah, it seems like it's probably a different presentation of the same proof. Maybe I can present the same proof in Italian or in English, or Euclid proof. Some people say it's a proof by contradiction. It's not a Euclid proof by the infinite many primes. But like it depends, are you interested in the main idea or in the logical structure or like in the historical accuracy? So there is evidence for the fact that there are no context-independent identity conditions for proofs. It's going to be dependent on what we're going to do with these things. So MacLean said, and many others thought, okay, maybe we should identify proofs following like the main idea. Say a proof is not just a series of individual steps, but they are together for a plan. So we affirm that every mathematical proof has a leading idea which determines all the individual steps. So it's like a plausible thing is to say, okay, if the idea is the same, then those things are two different presentations of the same proof. But in fact, like some could argue, wait a second, some cognitive differences or epistemic difference might be relevant. If you're pursuing epistemological analysis of mathematics, that is, if you're trying to understand in virtue of what exactly is a belief in a mathematical claim justified, or in virtue of what does that belief constitute knowledge. So that is like my epistemological inquiry, and I think in order to answer that question, you have to work with a finer grain equivalence relation of proof presentations. So here is Marcus Giaquinto, who's like trying to get at some of these issues. He says, usually mathematicians are happy to regard two presentations as presenting the same proof if the central idea is the same in both cases. But if one main concern is with what is involved in thinking through a proof, its central idea is not enough to individuate it. The overall structure, the sequence of steps, and perhaps other factors are going to be relevant. Even so, and this is like key, not every cognitive difference will entail distinctness in proof. And that's precisely what I was trying to get at when I distinguish between the enabling and constitutive properties of annotation. So a proof, obviously, like written in blue instead of black, it's going to be like maybe a different presentation of the same proof, or even maybe like the same presentation of the same proof, just like two different concrete instances. And so if we individuate proof in a way that is sensitive to the particular reasoning that we need to grasp its conclusion, then going from a topological proofs involving visualizations to a diagram-free proof would be a significant change, one that does not just change the presentation, but change the proof altogether. I claim there are plausible criteria of identity of proof according to which if we convert a diagrammatic proof into a non-diagrammatic proof, then we are not changing the presentation but the proof. And here, just to give you a sense, like the little steps I showed you before, obviously like can be converted in text. All this diagram can be converted into algebraic word where I use a convention Z for the zigzaggy like interruptions, and then you can just like write everything without diagrams, but the understanding would be obviously compromised, and the same is true for not diagrams. And also for this was a slide for arrow diagrams. So the diagrammatic proof presentation requires the reader to visualize specific spatial manipulation and recognize they are valid. The diagram-free proof does no such thing. And also for commutative diagrams, something similar can be said. So even like algebraic diagrams that are still diagrams because they are two-dimensional, obviously can be easily converted into linear displays, but again, we can't perform the same type of reasoning. So just a minute to two.
For some kind of easily.
Yeah, no, but it could be, no, diagrammatic reasoning can also be very hard. Also, like, we can have terrible diagrammatic systems that make it even more cognitively taxing. So that's not to say that all diagrams are good and the non-diagrams are bad. Absolutely not. It's also context dependent, what is good for what. So just like to conclude, diagrams can form notational systems. So I'm not saying that diagrams are always good, but diagrams sometimes are good, and we should distinguish diagrams from illustrations. The perceptual features of notational systems, both diagrammatic and not, can be divided into enabling and constitutive features should satisfy three basic constraints of clarity, reproducibility, and usability. So this suggests that diagrams can be used in proofs. Some diagrams exploit intuition in a regimented way, like diagrams for surfaces or not diagrams. Others are instead akin to algebraic notations. And from the perspective of mathematical practice, a significant difference in the overall epistemic and cognitive advantages of presented proofs entail that the proofs themselves are different. So these hold even if they have the same informational content. And so here I'm like curious about what you think about it, because this is actually very related with what formalization even means. So what is someone doing when he's formalizing a proof? It's like creating a different presentation of the same proof or creating a different proof altogether, and what does this even mean or entails? Therefore, I think from the perspective of mathematical practice or the philosophy of mathematical practice, diagrams in the proof, in some proofs, are essential to those proofs. So diagrams can be converted, but they get lost in translation. So that's it.